I have this how to say I have this title to make it more attractive to the audience because I think if you want to have a battery that can be used for the EV industry, you need to meet some requirements, including the safety as a first example. Second priority is the record free, and then of course third priority is low cost, and then final priority is the long range. So it's opposite than the original. All the people were thinking like, oh, you want to have some battery, have a high energy density, high power, everything like that. Instead, you should have a better safety, record free, and then that is acceptable to the whole market. Then you are talking about the performance. So that's why 24M is developing a solution to fulfill these missions. So I will have this our company's general overview as a starting point. Then we will introduce our four product currently we are working on. And then finally, we will propose the solution, how we can enable these four different factors. So our company currently has around 200 to 234 employees. And then we have more than 400 million capital raise. And then we have been doing the research since spin-off from MIT, starting from 2010. And then we have more than 700 granted and pending patents surrounding from the initial of the component till the end of the formation and also the pack assembly, whole coverage of the battery patent industry. And then we have the demonstrated cost advantage of the next generation battery production. And also we already have the currently semi-solid product sold in the market. And also we have 8 licensees currently working together with us to develop a gigafactory globally to dispatch these semi-solid batteries. So we have the high TRL level that is currently in the market. We also have low TRL level that is currently under development. So on the right side, we are showing our partner. On the left side, we have our milestone demonstrated to the market. So like I mentioned before, so safety is the first priority, and then the cost is the second priority, sustainability, as well as the range and efficiency. So that's why we integrate this full suite to make sure we can achieve every component level till the end of the total solution to enable all the requirement that's used in the EV industry. So we break down into 4 categories. So first one is the semi-solid currently at a high TRL level that we are currently dispatching globally as a gigawatt factory level. And then our next generation concept for the semi-solid is we are trying to demonstrate a closed loop direct recycling of the semi-solid electrodes to enable a recycling of up to 80% or 98% of total material to have close to lead acid replacement or lead acid battery level of cost demonstration. And then second one is our main topic today is mainly talking about this unit cell structure as a new cell format rather than the old cell format. We were talking about the prismatic or can or like pouch or cylindrical. We just use this very thin electrode as the cell, and then we demonstrate a unit cell ETOP structure to make the highest packing efficiency globally in a module level and pack level, and demonstrate a streamlined process and decrease material usage, especially the reduction of air cooling channels and liquid cooling channels. And also we also demonstrated some sort of like direct welding into the pack system rather than busbar connections. The third part is our newly developed technology. We invented a separator that we call it Impervio to demonstrate a Dendrite-free cells and also early fault detection and fail-safe mechanism of the battery. So we can detect dendrite growth. We can monitor the cell SOH at the in situ level. Finally, when we have the event that's unpreventable, then we'll trigger the VMS to trigger a fail-safe mechanism to discharge the cells into a lower SOC stage to ensure the safety of the cells. So combine all these together, we will currently focus on the development of lithium metal cells, and we invented a new electrolyte that has a very high conductivity of the electrolyte, and then the highest record-breaking liquid electrolyte transference number to match up together with the lithium metal system to demonstrate in the future if it is applicable. Then we have on the safety that's guaranteed, cost that's guaranteed, and record can be free because we can have an institute demonstration of the battery cells monitoring. Then we'll enable the lithium metal into the EV fields. So this is a whole table of our technology suite. We are starting from SemiSolid, then we spread out to the different component, and then we spread out to the upstream and downstream. And then we are also touching the next generation products. So I think we will start from the SemiSolid manufacturing platform. This is our initial innovation since 2010. So currently we have 8 licensees globally, and then we have Kyocera just got the first product launched in 2019, and then they were selling around 200 megawatt to 400 megawatt cells per year with an ESS storage system to match on the home storage system. And we have an Oroplus, which is the Asian battery maker. They were under a PTG group with the utility company to sell an ESS unit in the Asian factory. And then we licensed the technology to Freyr, which is the most favorite SemiSolid manufacturer right now in the market. So they just finished the CQP line first cell production, and then they were under the production ramp-up period right now. And in China, we have a licensee called Asiva, which is mainly working on the FAT stage. It's just finished, and then they will bring in all the factory equipment into the factory with a gigawatt-hour factory range, mainly supply for the EV applications. Then in India, we have Lucas TVS. It's working on the land selection and also build the cells. And then Freyr announced the feasibility of the US manufacturing in SemiSolid format. And then finally, we have our global partner with Volkswagen Group to see if we can use their platform to launch the SemiSolid product in the EV applications. This is our current progress, one of the successful process journey with Kyocera. Initially, we start the collaboration since 2015 together with them, and then they launched their first product in 2019 and sell the product around 200 megawatt level. And then this year, they double the production of the capacity to 400 to 800 megawatt hour range. And then they were trying to still sell the ESS unit with the SemiSolid format, initially at 5 kilowatt hour range. Right now, they were targeting around 25 kilowatt hour range. And then because of that, they were together awarded Japan and Electrochemical Society Award together with our CEOs. How the SemiSolid work? So our process is quite different compared to the conventional process. We're using electrolyte mixing together with the powders and then to form a clay like a cookie dough like slurry with a high yield stress. And then that high yield stress non-Newtonian fluid was piston pressed onto the current collector. Then after the casting, we direct to the winding and packaging because electrolyte is a processing solvent. And then from mixing till the casting till the assembly, it's minutes of operation. So when you have the powder, and then you have the powder mixed together very well to ensure the uniform slurry properties, then you can build a cell within minutes and form them right away. From the beginning till the end, there's no drying step to remove the LNP. There's no binder to bind the slurry to the current collectors. So this is one thing everybody is asking me quite a lot during my journey. So why you can stick them together? So you can think of the clay is with the carbon material mixture, and also the cohesiveness is quite strong. So we tune the slurries to ensure the cohesiveness, co-adhesiveness to become the maximum. Then it can be adhesive to the current character very strongly. Then we can even bend, we can even roll, we can even assemble and flip the electrode without any questions. So the robustness was confirmed with shock and vibration tests, and also lots of tests was done, and also that's why we can see the product in the market that can pass most of the tests. So robustness part, it's magical and hard to believe, but it's a reality. You can buy it in the market. So because of this innovation, and we see that in the beginning there is no binder, and then the slurry itself, it become a black mass. Because of that black mass behavior, we are trying to use a method of direct recycling or closed loop recycling of our semi-solid families. So what we were doing is we commit cell at the beginning, and we can commit return back to collect the black mass or end of life cells to wash it away of the most of the inactive component, then the active component, because there's no binder removal process in the beginning to the end. And then the damage to the active material is minimum. Then we can demonstrate, especially for the LLP case, when we have a 3,000, 4,000 cycles LLP, we do a direct wash, and then we tear it down, we do a releasation, then the whole cell become the original materials. Similar behavior we can observe from the graphite side. So SEI wash, and then with minimum cooking, then you can recover around 90% to 95% of the original capacity. So most active material can be fully recycled. Then with the direct recycling cost modeling from one example, then we can gain a benefit from the recycling, especially for the LLP cells. And demonstrate a full loop of a closed recycling and reduce the dramatically cost. Cost reduction is done, then we will focus on the energy density improvement with this Electrode-to-Pack structure. So first thing is we found that currently in the market, there are one way. They have one way to have the cell as high energy density as you can. So basically when you put the electrode, you put the electrode into the jelly roll, and then you put the jelly roll into a can or to the pouch. Then the can and pouch become a module pack. So the best scenario they were currently showing is around 72% with the CTP structure. But that was the cell to the pack efficiency. You still need more than 500 to 800 cans in this pack. Those cans will become your burden and reduce your energy density quite a bit. Our concept is because we have SemiSolid at the beginning, and well electrolyte confinement within this unit cell bag structure, then we use this bag structure to put it directly into a pack. And then we do the series connections within this whole pack structure to mimic any jumpers at all from this pack manufacturing. Then the electrode level of these cells is really, really high energy density in various formats. Then there is a reduction of a BOM cost, CapEx assembly, because the pack manufacturing become a cell manufacturing, and then very high energy density, of course. And then for semi-solid nature, you don't have electrolyte injection step. You can do whatever size, whatever how big you can be with this unit cell structure. There is no physical limitation of this electrode casting on the cell assembly process. Then you can make this cell like this demonstrated pack or module, we call it. It's around 96 volt, and then this is 1 meter with a 50 centimeter module. And then module packing efficiency including the cooling structure and also BMS, could be higher than 80%. So with this roadmap, we demonstrate our various chemistry from the LFP grid application into the thin lithium air with the high nickel applications. So this is 1 per liter we can achieve with the pack level, currently developing target. And then like 2024, we achieved the LLP pack with the ETOP structure. And then we are ongoing with the nickel 80. So right now, we will start to demonstrate nickel 80 with the Electrode-to-Pack structure in the near future. So with this concept and integration with a large format unit cell, we demonstrate a carpet unit cell specification of the electrode, LP, ranging from 320 to 440 watt per liter. And then with 78 to 80% with the LP pack efficiency, we can easily achieve 250 to 350 watt per liter. Then we can use the LFP graphite cells to compete with the MC graphite cells, and with a very low cost reductions. And then and relaxed safety and also the cooling needs. And if we integrate it into the MC system, we can easily achieve more than 350 to 650 watt-hour per liter pack level demonstration. Then in this case, per kilowatt-hour charge can be very, very high. With all the platform integration, we further reduce the total cost. Initial cost reduction with the SemiSolid integration, it can reduce the BOM cost, processing cost by 25%, and then cost saving of the other cost around 50%. Then with the pack integration and also the end-of-life cell recycling, we can further reduce the total cost by 1/3 of the active materials. And the pack cost around 1/3. Then finally, we need to address the safety issues. For the safety issues, we need to have the reality that battery is not safety-wise. So you can see tons of recall, tons of fire currently in the market. You can see like Tesla cells has around like 100K miles, and then you tear down the cell, you see the lithium growth inside the separator. That cell is at we call it a rollover stage, and then it will be easily caught on fire within abusive case. So you see the lithium-ion battery caught on fire again and again, and then you see lots of recalls happening with the Samsung SDI recall in the Note 7, and also recently LG Chem continues to recall about the Volt, that type of situation happening. And because of that, especially for the overcharge case, it's happening a very dramatically backfire. Like this electric bike battery fire is during the charge stage, and then BMS is not controlling the cell well, then it triggered the whole cell explosion. So we have seen this continuous ongoing, then we need to solve the issue. So Dendrite is the main issue we saw to cause these whole fires. So for the fast charge cells, you can see the anode graphite at the beginning. If it's slow charge discharge, there's no lithium plating, there's no dendrite growth. But when it goes to the charge discharge at a very aggressive stage, you see continuous lithium growth, and then it becomes irreversible in the end. So this is a lithium growth at an insistent stage, and then you see a long time use when the anode is failed, and then you see the lithium growth too. So lots of strategy was using to plot the lithium dendrite growth. Most favorite method is the solid-state electrolyte. Solid-state electrolyte won't bother the dendrite growth at all. And then liquid electrolyte, everybody know you will have dendrite growth. So then our strategy is the first thing we introduce this brand new separator that can monitor the cell voltage and then cell health. And then we introduce the dendrite on purpose. So the first dendrite we're introducing is a metal dendrite that during the manufacturing. So this metal dendrite during the manufacturing has lots of powders, and then it's shot right away, but this one can demonstrate long cycle life. And then we have the defect cells, have the dendrite growth. It's shot right away at the beginning, but with this Impervio, you can block the lithium metal growth put through a separator at all. Then we do another very aggressive test. Basically, we overcharge the whole cells. And then when we're doing the overcharge, the lithium will continue to go from the cathode to the anode, and then plate lithium around like 100 times more comparing the design. So it will definitely short. So you can see this competitor cells, I cannot name it, but you can see that it fail like blow up like hell. Then we introduce this Impervio because there's no internal shot from beginning till the end. They pass on test, and then we tear it down. There's no burn, no dendrite growth cell. So then the most favorite test is the nail penetration. So we do a nail with 32 pin. Initially, for the regular nail, it blows. But for this one, we enable use a DMS, lower the SOC quickly, and then there's nothing happen. So this is one of the transforming technology we'll try to introduce. Then we bring it to the lithium metal. So we introduce one new electrolyte with a high current exchange number. That electrolyte can cycle the 20 milliamp per square centimeter charge discharge without any shock, and the ASI grows. Then we demonstrate it in the 1C MC lithium charge discharge continuous cycle for more than 500 cycles without any shock. Then we bring the copper away, and we use the lithium as the carrier and the current collector. Then we laminate lithium to our outside PET film and demonstrate a 550 watt per kg commercial roulette ready around 3 ampere hour cells. And then that cell is around like 4 cells together. And then we can see that 4 cells is still under cycling right now. It's 100 cycles. We reduce the charge rate to ensure there's no too much more silicium to cause the disconnection, but the power doesn't lose. So discharge power can still achieve around CO2 range without any sacrifications. So we still monitoring these cells, and then we were demonstrating higher and higher ampere hours. So first target we're using is to demonstrate that in the Alpha E EVs for all or the scale-up project to see if we can use it for the EVTOL applications. With all, then combined together, we do a feasibility study with the module assembly using the Electrode-to-Pack structure with this large format of the conventional cell or narrow format with the lithium metal cells. With the narrow format lithium metal cells, we reduce the Electrode-to-Pack efficiency, and with reduce the or clamping of the structure, so to make sure the high pressure can be applied to the lithium metal. And then we reduce a little bit or sacrifice a little bit on the Electrode-to-Pack efficiency. But we can still achieve more than half or 1/3 of the weight, can still achieve around 1,000 kilometer drive very easily. And this form factor is still under studying with lots of cooling designs ongoing, and then we are demonstrating that in the near future. With all, I conclude my talk with all the services we were providing, from the cost reduction to the safety enhancement to the energy density buildup, and with all the combination of the technology suite, we're trying to ensure in the future we can have a low cost, high safety standard, record free, and 1,000 mile per charge pack. That's all I talk. Okay. I have time for the questions. Any questions?
Hi, Junzheng. If you don't mind, I can ask a couple of questions.
Yeah, go ahead.
Thank you for the presentation. If I get it correctly, in the SemiSolid slurry design, the active material is being mixed with the electrolyte, or you are not using any NMP, right? It's the electrolyte that kind of fluidizes the active material. Is that correct?
Yes.
And then you mentioned that it's, I mean, you made an analogy with clay, how the clay actually forms something solid eventually by wetting. Well, the analogy is probably very close. The difference is in the clay we have a lot of hydroxy bonds formed that eventually they kind of fuse grains, separate grains through oxygen bonds, because the clays are mostly metal based, and the water is, let's say, uh, it's a hydrogen bond forming molecule, and eventually we can form this metal, oxygen metal, that kind of puts everything into a solid form factor. In the context of electrode materials, especially the LFP, we are talking about transition metal like iron, phosphorus, oxygen, lithium, and then the electrolyte is not really like water where you can form chemical bonds. So how does this interaction with the electrolyte actually solidifies the active material, and how does it, more importantly, how does it stick it to the current collector?
Yeah, so I think one thing is that chemical bonding is one way, but to be fair, AMP or the PVDF binding to the powders is not chemical bond forming as well. It's also sort of like a polymer wrapping structure. So then in this case, we were using carbon black as a wrapping structure to serve as a holding of the powders together to form a clay. That's the first structure. Our first strategy. Second strategy is we use high shear mixing to ensure the liquid is fully wetting to the surface of the active powders. So to keep in mind, so if the liquid electrolyte is not wetting your active material surface, you won't have electrochemical reactions at all, because there will be always a contact angle less to the liquid, between the liquid and the solid interface. So you want to ensure the full immerse of the liquid electrolyte onto the surface of the active materials. So by that means, with the liquid solid full immersed, that wetting can become better. And we remove the binder, and that means the tortuosity of the whole electrode become better. So we are targeting around 20% to 30% of tortuosity reductions. So at the same uniformity and the same thickness, we can actually see a faster lithium diffusion into the whole cells. And then talking about the bonding of the current collector. So we have two strategies as well. So first one is BET, surface area of the cover, can absorb this active material to the current collector. Second thing is there will be a wonderful force between the liquid of this type of non-Newtonian fluid when you apply the slurry onto the collectors. So two forces can form together and they can bond the current collector quite well. So I cannot show the video because of the confidential information, but in general, we pass all the EV required tasks. So and also sort of like shock and wipe, tear down, that type of tests. So cohesiveness at the beginning of the production and during the cycle is no problem. And then after the formation, after the SCI formation, there are more chemicals or more organic chemical that can serving as the bonding chemicals. That part will step in. So then you will see a better and better adhesion, especially on the anode side.
Well, thank you very much. If there's time, I can ask more questions, but I let now, everyone else in case they want to ask their questions. Thank you.
Yeah. Please go ahead.
Okay, if there's no question, I can actually ask one more. So I'm working with Aspen Aerogels. We are actually neighbors. We are in Northborough, Massachusetts. I'm leading the LFP research team at Aspen, and our value proposition is to embed nano LFP inside carbon aerogel to achieve very high charge rates. Recently, we got funding from the DOE, so we are actually moving on to the pilot scale. What I realized by working on LFP carbon aerogel electrode is that they are fundamentally very different from the typical LFP that you can get from the the manufacturers. The big difference is that the carbon aerogel is actually, first of all, it forms a scaffold where the LFP is embedded inside, so it's not just a coating that coats the active material. And also, it has a very high surface area. So what we realize is that normally you, when you add the NMP and the PVDF, they behave in a very different way because of all the surface area. So my question is, do you think that this technology of semi-solid slurry preparation, or maybe I shouldn't call it slurry, but would it also extend to other evolving newer architectures of electrodes? In EPS, would your company be interested in testing some of our materials? And I think actually the carbon aerogel technology platform is very much well suited for thick electrode coating, knowing that there is a lot of porosity inside. So you can actually go very thick and load a lot more material without actually introducing extra current collector. So what's your take on that?
Yeah, so actually we have NDA in place. Initially, we test your silicon material, but I don't know your silicon status right now. So,
Right.
one more thing is, I think please keep in mind that these type of like a new material, especially for the non-analyzed material, you will encounter some sort of like BET associated issue, right? Especially for our process, we are very sensitive to the material morphologies. So we are open to test various type of material, especially for the materials that is not common in the market. So our working strategy usually is we work together with I won't do the APQP process for these type of joint general agreement. So what we'll do is we'll test materials and feedback to you what type of gap we have in between each other, and then we'll see what we can integrate in the near future. In general, we are open-minded. So what we were doing so far is we will help the initial guys because come on, we're a battery company, so our battery sales must be better than yours, right? So we can provide you better battery test results, and then we can help you to design the batteries that semi-solid format or other formats as well. So we're open to that, and then please talk to one of my engineers, and then I can introduce that to you later, and then we can go from there. But for the LP materials, I think the main difficulties we had is volume. So we were talking about like gigawatt of factory right now. So if you're small scale, then for the qualification, even if you can ramp up quickly, so it will still be, let's say, next 2 to 3 generations down the road.
Thank you.
I had a question on, so you had mentioned that your costs are much lower per gigawatt hour of cells produced, right? Like, I was wondering how the throughput compares, like how many gigawatt hours per year one of your lines can do versus the conventional lines.
Yeah, so I think in general, our line capability will be larger than the others because we have reduced the processing step. So depends on the different chemistry, and also our aerial capacity for the ESS market is quite thick. So our aerial coating for the electrode is around 2-3 times thicker than the others, and then we don't have drying step. So per line, so that's why like CQP line is in Freyr, and also Aziva in China. The line is very compacted, so there's only one line. They can meet the mission around 1 gigawatt hour, and but the owner line needs to be compacted because at the beginning we introduced the Eternalyte. So that's why this step is combined with each other, and then our main collaborator is mainly working on the equipment development and to ensure the closed loop. Yeah. For the detailed line size, maybe you can reference Freyr's report. They have some details over there, like how large the coating line, how large the dry room they will use, and how many steps they have.
Okay.
Mm-hmm. So I think I saw another question about the DCIR target for the 21 cells. Fast charge, high rate discharge, heat generation, that type of questions. So I think so for the EV application, our strategy is we reduce the thickness to like 2 times our conventional electrode coating for the single-sided electrode. So in general, the coating let's say conventional electrode get around 100 micron per layer, and then they are double layered. So it will be 200 micron for one current collector. So then wheel coating will be 200 micron single layer. So then with the 30% of the tortuosity advances, and then with the high electrolyte conductivity, then we can make up the difference. So DCIR target of the cells, we currently for the NMC cell, we're targeting to meet the original target that our NMC cells currently sold in the market. And then the fast charge capability, we have various solutions, but when you go to the very premium market, let's say have fast charge, high energy density, everything together, we tend to do the next generation chemistry demonstrations. So for that purpose, we demonstrate the fast charge capability for the silicons, fast charge capabilities for the lithium metals. So that's why for chemical application, our main application currently is EFS and low.
Going back to the previous question about the throughput of your new process, it's that the throughput is driven by the takt time rather than the number of steps. Does your process increase the takt time for your thicker coating that you mentioned?
Yeah. So first thing is mixing step is direct. So our current limiting factor is not coating, it's not the slurry mixing steps. Our main limiting factor for this electrode feed is the stacking and winding step. So I have a background noise. I need to mute some. So in this case, most of the winding and stacking is the limiting factor. So with all the other factors, can be smoothly go through. And then if we improve the winding and stacking steps and the back end, then we can increase the speed of the whole cell manufacturing. Because the total step is only 6 steps in total. So in general, we doesn't care about the coating speed or stacking time. So what we care more about is the unit cell assembly step. And when you have this bag formed, the cell is done. So in general, we call it the line speed limit.
Okay, thank you.
Alrighty. Thank you for attending my show. If anyone have any other questions, you can connect me through the LinkedIn, or you can send me an email, or reach out to me whenever you have any chance. Okay, we will have a multiple presentation this year with various battery meetings. You're welcome to attend our booth, and then you are welcome to attend our talk to see our new progress. Thank you.